All right, let's talk some stats here. Chapter 6, this is section 2, a binomial probability. As many of you should remember, binomial means 2. So let's talk right through an example right off the bat and go this route with it. So Shaquille O'Neal, we're all familiar with him. If you've seen his show Shaq Life on TNT, it's kind of entertaining. Check it out once in a while. It's kind of funny. Anyway, he shot a career 52.7% from the free throw line. Probably not the best, especially for a big man who's getting fouled all the time. We want to determine the probability that if he shoots 3 free throws, he's going to make 2 out of 3 of them. Okay, well, what's going on here? What are we trying to figure out? We got 3 free throws, and he's got to hit 2 out of 3. So what's our sample space going to be? It could be make, miss. He could make the first one, miss the second one, make the next one. He could start off and miss it, and then have 2 makes that follows. All right. What's the probability that he's going to make a free throw? Well, that's told right here. He's a career free throw shooter of 52.7%. So 0.527. What's the probability that he misses? The complement to this, 1 minus this. So this is a miss in this case, not the variable x. So a miss probability is 0.473. So as we're figuring this out, recall, this one goes back a ways, I know, I'm aware. But we want 3 makes in a row. So we need I'm sorry, I said 3 makes in a row. We need 2 of the 3 to be makes. So a make, and a miss. Does it have to be in this order? No, we could do this one, then we could do this one, but we need this, or this. Or the simplification of this is take it to the 3rd power, all of our different scenarios that could happen. So, probability of Shaq making 2 out of 3 is 0.394. So you're a coach, you're working at analytics, you see this, you know that at the end of the game, also, factor in tiredness, who do you want to put on the free throw line? Well, chances of him making 2 out of 3 are 39%. Probably him, or if you got somebody else on your scouting report that's lower, then that's what we want to do. Put those people there so we have a chance to succeed. Okay, so now let's talk about this binomial probability and different things that are going to help us out. Maybe some little shortcuts that we can work, if you will. First off, from the reading, you read up on it in the book a little bit. But for a binomial probability experiment to happen, 4 things. You got to have a fixed number of trials. The trials are independent. Okay? There's only going to be 2 outcomes, either a success or a failure, depending on what is defined as success or failure in the problem. So this is a disjoint thing. They're mutually exclusive of each other. Remember what that means. Bi means 2. And then the 4th thing is the probability doesn't change. It's going to be the same for each trial. Going to be the same for each trial. An example. You want to roll a 5 on the dice. Well, what's going to happen? Either you get it, you do roll a 5, or you don't roll a 5. Either you do or you don't. Binomial. One thing or the other is going to happen. Let me change papers. So, as we're doing these binomial experiments, what do we need? Well, let me put this in the right spot. There we go. So, what's needed for a binomial probability? You've got the checklist to make it. Now, if we know it's going to be, what do we need? We need number of trials. We need the probability of success and the probability of failure. But as you recall, those would be complements of each other. 1 minus something would be the complement. And then we want the number of successes that you're looking for. Now, notice it's worded that way, because if you're looking for how many times you can't get something, well, technically speaking, that would be a success. Just keep in mind how it's worded and what you're looking for. So our formula for binomial probability distribution is this. It looks somewhat complicated, somewhat complex. It isn't. It takes a little bit in terms of steps, but it isn't. We got our combination, so our calculators will help us there. That's the probability raised to the power of x. There's the complement raised to the power of n minus x. So that's our formula that we want to remember. Taking in all the possible combinations could happen. Probability of happening times the probability of not happening, or in other words, its complement. So, word-wise, the probability of attaining x successes in n trials with a success of this probability is blank. Let's go back to our shack problem. The probability of getting 2 made free throws in 3 attempts with his success rate, in other words, his free throw percent shooting of 52.7%. Here's how that translates. Number of trials, probability of succeeding, and what we want. We want 2 makes. So we'll set this problem up as such. Combination, 3 attempts, 2 we want. Probability of success, complement, or in other words, I just did a little bit of work here, raised to that power. We still get our same decimal of 0.394. So somebody's going to sit back and say, well, gee, why don't I just keep doing this all the time? Because the problems are going to get more complicated than just this. So we'll show you. So this formula, once again, combination, 2 out of the 3. That takes all your different scenarios, so I don't have to be raising things all sorts of crazy ways. Success squared, failure to the first power. All right, 0.394. Very good. All right, let's see what we can come up with here. Let's go with an example here now, and we're going to make a distribution chart out of this. Let's just say, for our example, we're in a problem, and there's 7% of the population is type O negative. I don't know for sure. I might have just kind of made this one up off the top of my head. But 7% of the population is type O negative. We take a random sample of 6. So we've done a random sampling, and it's 6 out of a certain number of people. And with a blood type O negative. And we were going to record it. We want to construct a probability distribution for the random variable. That in this case is x. So x would be 1 person has it, 2 people have it, no people have it, 3, 4, what have you. So we want to make sure we're labeling things as we do this. Well, what's our success? Well, we know 7% of the people. So there. What's our failure rate? 0.93. N, our sample size is 6. And then x, that's what we're trying to figure out here a little bit in terms of what's chosen. So as we set this up, notice what we have going on here. X would be 6 of them do, 5, 4, 3, 2, 1, or nobody that we choose in this sample has that. Okay? Our formula, right there it is. So the probability, 7% of the population is type O negative. Probability that we choose randomly 6 people, and they're all type O negative. Well, in terms of logic, you should be thinking to yourself, well, it's probably not very likely that that's going to happen. Well, here's the math behind it that proves that you're right. It's not very likely that it's going to happen. Look what we did here. And I want to go through these so hopefully you see something happening. Patterns. Combination that all 6 have are O negative. So 6 out of 6, There's our success rate raised to the 6th power. There's our failure rate. Well, we don't want any failure. That's why it's raised to the power 0. Anything to the power 0 is 1. And we do the math, we get that answer. Highly unlikely that all 6. All right, there's your percent. Yeah. All right, 5 out of the 6. 6 people. 5, we don't care where. That person that isn't could be first anywhere in the positioning. Think of make, miss, make, stuff like that. Again, success rate, now to the 5th power because we want 5 of them. Failure rate to the 1st power because 1 of them is going to fail. Still minute, but it's a better percent than that. Probability of getting 4. Okay, there's your combination. Success because 4 of them. Failure, 2 out of the 6, so that's why it's raised to the 2nd power. Becomes better. All right, half of them, 3 out of 6. Excuse me. 3 out of 6 are type O negative. Well, we look. There we have it. There we have it. Again, look at patterns. Look at things that are happening. These exponents add up to be how many people are in the sample. And again, get better. Still low. I mean, come on. 7% of the population. Probably 2 of them. All right. 1, 2. We're up to a halfway. I shouldn't say halfway, but we're up to a percent. 5.4% to be exact. Probably that 1 of the 6. All right. Higher likelihood that 1 of those 6 will be. Probability that none of them will be that type O negative. Well, success is this, none. Failure is this, all of them. So about 65% chance that's going to happen. There's our work that's going on. It takes time to set up. It's nothing you can't do. It's just the fact of it takes a little bit of time and working through the steps. That's all. So there is our probability distribution for the random variable, or the binomial random variable, BRV, if you will. Binomial random variable.